protocol for us. So it's like a little bonus. We don't have to actually manually turn on LDP. If you enable MPLS, it's on by default. And when we enabled MPLS, each of the routers took all of the routes in their IPv4 routing table and they assigned a local label to each of those routes. So for example, if there was the network 7777/32 somewhere in the network, router 2 would go ahead and assign a local label that it associates with 7777. And in our lab environment, we constrain the range of labels for each of the routers so that all the labels that R2 generates start with the number 2, and all the labels that R3 generates start with the number 3, and so forth. So where we're going to pick up is I'd like to spend a moment right here regarding creating local labels. And in a lab environment, I think it's important for you to see labels change. So you're not just thinking about one specific label that goes with one network all the time. Because after a router reboots or you disable and re-enable MPLS, those label values are not going to stay exactly the same. For example, the 777 network, on one day it may be 325, and on another day, for example, after some kind of a change in the configuration, maybe it's 381. There's a lot of factors involved. When the router came up, how many routes did it have, how many labels did it have to allocate, and as those variables change, and as the routers come up and enable MPLS, they won't use the exact same label every single time for a given network. So I want to walk you through how you can change in your lab environment the labels that are going to be used to kind of mix it up a little bit. So we can still have R3 use the range 300 through 399, but maybe we'll mix it up so that we aren't using the exact same label. And the reason that will assist us is because it'll help us focus on what's really happening and not memorizing a specific number as a label for some network. And then what you and I will do is we'll take a close look at the detailed play-by-play back and forth for setting up and establishing an LDP neighborship. Because once that LDP session is up, for example, between R2 and R3, they can start to share their local mappings of their local labels associated with the networks with each other. And that's really important because if R2 doesn't know what R3's local mappings are for various networks, it won't be able to impose the correct label when it's forwarding an MPLS packet over to R3. So the sharing of labels is a precursor or a requirement for each of the routers to build its correct and most efficient MPLS forwarding path. Now the first thing we got to do is just make sure, like when you bring up your rack or your lab environment for the first time, just make sure the IPv4 network is all functioning properly. So from R1, let's do a quick trace over to 5555. There's all of our labels being shown up in the path. That looks great. So we want to start with a nice healthy network. Next, let's go right at the middle, over to R3. And on R3, let's go ahead and take a look at all of the labels, the bindings that currently R3 is aware of, both local as well as the labels, the remote labels that have been advertised from R2 and R4. So if we scroll up, the actual syntax for that is show MPLS LDP bindings, and that's showing us everything. Now if we scroll down just a little bit, here we have the entry for 5555, which we know is the loopback address over on R5. And what this says is that from R3's perspective, now we're sitting at R3, that the local label R3 is associated with 5555 is label 305. And it just so happens that R2 and R4 also use that same exact last digit of 5 for their local labels. And that's because in this controlled test environment, I've got a fairly simple routing table across the board, and I brought all the routers up at the same time. And so as they started grabbing labels and associating them with networks, it appears they did it in the same order, and that's the only reason why that last digit is the same. There's nothing magical about the last digit of 5 being associated with this prefix. It just happens to be the label that each of these routers generated for that network. Now, if we wanted to ask Mr. R3, hey, can you just show us your local labels? Don't show us all the ones you've learned, just what you know about personally. We could do the command show MPLS LDP bindings with the keyword local at the end. And here we'd have the local bindings. So for 5555, our local binding is still 305. Everywhere we see an implicit null for a local binding would imply that we are directly connected to that network. So 3333 is R3's local loopback, and 1023 is the directly connected network between R2 and R3, and 1034 is the directly connected network between R3 and R4. Now when using Ethernet interfaces, we're using something called frame mode MPLS. And when using frame mode MPLS, we're going to use something called per platform label space. And all that means that in this case, if R3 is using label 305 for 5555, and let's say R3 has a whole bunch of different interfaces talking to different routers, it's going to be consistent in advertising label 305 for 555 across all of its interfaces. It's per platform. So you and I might ask the question, what other possibilities are there besides per platform? Well, if you're using something like ATM, you could potentially do something like interface-based label space, where you could say I have network 5555 in my routing table, and on one interface maybe you have label 306, and on a different interface you have label 307 in the context of the specific interface that you're using. But for Ethernet, like we're doing here in class with frame mode MPLS, it's going to be per platform and one label per network, regardless of how many interfaces we're advertising on. Now, one of the challenges that I've seen is that people in a lab environment where it's static the whole time sometimes get associated with one specific label and say, okay, that label I know goes to this network. In a production environment, labels are going to be all over the place. For example, if a router comes up on Tuesday and it's got 2,000 routes, it's going to have 2,000 labels. And on Friday, if there's 6 or 7 more routes and there's been a reboot or a reset of MPLS, it's not guaranteed that we're going to have that same label associated with the same network anymore. These labels, in R3's mind, are only locally significant. And if it wants to change its mind about a local mapping based on a reset of MPLS, it could do that. And through label distribution protocol, we would advertise to our neighbors what our new local label mapping is for a given prefix. Now, to demonstrate how the labels can change, let's take a look at what we could do to mess this up a little bit. Here is the local label currently for 5555. It's 305. If you and I decided that we wanted to disable MPLS temporarily and then re-enable it here on R3, R3 would then have the opportunity to assign a brand new label for network 5555. And if we disable and re-enable fairly quickly, it's very likely it will choose a brand new higher numbered label for 305. So our next steps would be to disable and enable it. So to disable MPLS, we'd use this global config command, no MPLS IP. And then we could re-enable it with MPLS IP. You'll notice we lost our LDP neighbors. And then very quickly they came back up because we were then running MPLS again. And now what I'd like to do is let's verify whether or not this local label of 305, which R3 was using, let's see if that's changed to something different. So now if we issue the command show MPLS LDP bindings local, it's going to show us all the bindings. And there's our 5555. You'll notice it's now labeled 309. It's not using the label it used to be using for that network. And if we wanted to take just a look at that specific prefix, we could do a show MPLS LDP bindings for 5555 with a 32-bit mask, and that would confirm it as well. So there's our local label of 309. You'll notice R2 and R4 haven't changed their mind about what their local label is because we didn't reset MPLS on those other systems, just on the local R3. So with LDP operating in the background, advertising all the information between R3 and R2 and R3 and R4 through their LDP sessions, R2 knows that R3's local label for 5555 is 309, and if we get a packet destined for 5555, R2 is going to impose label 309, send it to R3, who will immediately switch it out and put on top of it label 405, based on how MPLS has sorted out what the best path is to get to that final destination. And we could verify that best path so we didn't have to just guess about it with show MPLS forwarding for 5.5.5.5, and that'll show us. So it says my local MPLS label for network 5555 is 309. If I get a packet that's labeled as 309, I'm going to go ahead and swap out that label with 405, send it out gig 3/0 to my good buddy R4, which would cause a re-encapsulation at layer 2 with the layer 2 destination address of R4's Ethernet interface, and that packet would be sent. Another thing to know is that let's say a packet comes into R3 that's not labeled. It's destined for 5.5.5.5, but there is no MPLS label. R3 is going to prefer the label switch path over the IPv4 path. So what would happen is if R3 did get a packet, just a naked, normal packet destined to 5555, R3 is going to say, holy shnikers, you're trying to get to 5555? It would inject or impose or push on this label of 405, send it to R4, going out this interface on the local router, And then when R4 would get it, it would have label 405, and then R4 would follow his marching orders based on receiving a packet that had an MPLS label of 405. So if it ever comes down to using the label switching path or sending packets based on IPv4, if both options are present, the LSP is always going to win. Now, in a lab environment where we can do debugs without any type of harm to production systems, we could do a debug to help verify the details of what's going on regarding label creation and label advertisement inside of a router. So let's do this together. On R3, let's create an access list that's looking just at 5.5.5.5. Now, how is that going to help us? Well, if we do debugging and we tag on an access control list, it can filter that debug to just show us the results based on that information. So in our example, if we just want to see label and binding and advertisement information regarding 5.5.5.5, we can use this access control list 1 in combination with a debug. So the debug I would recommend you do is this. Let's go ahead and use debug MPLS LDP bindings and then simply throw on prefix-ACL1 saying only for things related to 5.5.5.5. And then we'll play the same game we did just a moment ago. We'll tell the router to forget the MPLS game just for a moment with the no MPLS IP, and then we'll tell it to go ahead and start it up again with MPLS IP. That should create a storm of activity regarding bindings and MPLS, and what we're going to do with the debug is only see results that have 5.5.5 as part of that output. And then because I don't want to leave that debug on, I'm going to go ahead and do a undebug all. And now let's take a look at the results. So if we scroll up just a little bit, here it's talking about I learned a binding from my good buddy R4. Let's scroll up a little bit higher. And right here it's saying it's now assigned label 304 to network 5555. With a debug like this, I kind of feel like a psychologist who just sat down with a router. Tell me about 5.5.5.5. How did you feel? I mean, every thought process, all the stuff that's going on regarding that network as it relates to MPLS LDP bindings is all right here. So the local label is 304 that R3 assigned to it. We learned a label from our good buddy R4. So R4's label is still 405 for that network. So if we receive a tag packet of 304, we're going to go ahead and switch it out with a 405 as we forward it onto R4. And we've also learned about a binding of 205 from 2.2.2.2, which is router 2's local label. And just to verify, if we want to just take a look at the bindings for 5.5.5.5, we can ask the router to show us that. And there's our local label, and there's the neighbor's local labels that they're advertising to us. Now the actual conversation that goes on between two routers as they are negotiating and setting up an LDP session is fascinating. And what I think we should do is let's go ahead and cause it to happen. We'll disable and re-enable MPLS on R3, and let's capture the traffic real time on this link between R2 and R3, and that will give us a very good picture of what's really happening with the LDP hello messages and the LDP session establishment. So to do that, I'm going to go into configuration mode on R3 again, and I'm going to disable MPLS IP globally. And then let's drag our GNS3 topology in, and what we can do when we set up GNS3 is there's options. You can go to View and go to Docs, and you can control whether you want to see the captures dock or the captures window, which is right over here, and all the other options. Whether or not you have the captures window open doesn't control your ability to use Wireshark with GNS3. If you've chosen the all-in-one installer from GNS3, as part of that, it installs Wireshark for you. So to capture the traffic, all we need to do is simply right-click on a link, for example, the one between R2 and R3, and say Start Capturing. Also, as an option, we can go to Edit and Preferences, and under Capture, we can say I want to automatically start Wireshark in the foreground to show the live captures. Otherwise, if we don't check this box, it'll just create the capture file stored for us in this location that we've identified for capture files. In our case, I'd like to actually see the Wireshark packets as they're coming in. We're going to do this live, so I'll click that checkbox and click OK. And let's go ahead and right-click this link between R2 and R3, and let's start the capture. It's asking me to choose an interface. I've got two to choose from, R2's gig 2.0 and R3's gig 2.0. Either one I pick is going to be fine because it's going to be the same traffic going back and forth. And we'll click on OK. That opens up Wireshark, and the packets are now capturing. So I'm going to put GNS3 off to the side just for a moment here. And then back on R3, we'll do an MPLS IP. to turn on MPLS, and it should reestablish those neighborships. And we have all of that captured right here in Wireshark. So now that that's done, I'm going to go ahead and hit the stop button in this capture. I'm also going to go back to GNS3, and I'll show you this. On GNS3, I also want to right-click here and say stop the capture. Otherwise, it's still running in the background. Or we can go to the captures pane, right-click here, and say please stop all captures. And then I'm going to dismiss GNS3 once again. So in Wireshark, which is just a fantastic tool to find out what's really going on, we captured 37 packets, and we can filter this. We can set up filters to just include LDP traffic or traffic just from certain ports. And I'm going to go to the very top of the capture. There's a shortcut for that. We can use this icon right here called please go to the first packet. And here is an LDP hello message. And let me go ahead and bring this full screen. And we could size this up if we wanted to. And we could create some filters. In fact, let's go ahead and create some filters just for a moment. With LDP, let's go ahead and select that first packet right there. This is hello message. And the hello messages, if we take a look at layer 3, it's from the actual physical interfaces. So in this case, it's a hello message from R2 at 10.23.0.2, and it's sent out to the multicast address for all routers. So in this LDP hello message, it's sourced from the IP address of the physical interface or logical interface that's actually sending the message. In this case, 10.23.0.2 is the IP address of gig 2/0 on R2, and it's being sent out to the multicast address for all routers. So any other routers in that same broadcast domain would be able to hear that, and that's part of the discovery process for LDP. We see each other's hello messages. At layer 4, we're using UDP, and we're using port 646 as the source and 646 as the destination for these little hello messages. Inside the hello message, if we open up that payload, it has the label switch router ID, which is 2222. And again, that's based on the highest IP version 4 address on a loopback interface when LDP is started, which also equates to when MPLS is started. And the label space of 0 represents we're using system-wide label space, not per interface, but per system. So whatever labels R2 has for a given network, it's going to be that same label advertised across all interfaces that are participating with LDP. And if we dig further into the hello message, it has something called a transport address. So let's say another router saw this LDP hello and said, hey, I want to build an LDP session to you. It would build the session to this IP address, the transport address. It would not build the session to 10.23.0.2, the interface that sent it, but rather the transport address, which in this case is exactly the same as the LSR router ID. And the good news is 2.2.2.2 is a reachable loopback address on R2, so everything's good there. So what I'm going to do is I'm going to build a filter as we go so I can just capture the packets that are relevant to our discussion, and then I'll save that as part of our Nugget Lab files. So I'm going to say for user datagram protocol, source port equals 646. I'm going to say prepare as filter. I'm going to say selected. So when you say prepare as filter, that means please help me build this filter, but don't apply it yet. So anything where the UDP source port is 646, and I'm also going to go down here for the destination port of 646, and I'm going to say, please prepare a filter. I'm going to say, or selected. So it's going to say, okay, UDP source or UDP destination 646. So when we finally apply this, it'll get all those hello messages. So there's another hello message, packet 5. So let's scroll down a little bit and get something a little bit more exciting. Okay, ooh, this is exciting. So we have some hello messages, and then we have a TCP session from 3333 to 2222. And here's what happens. When two LDP neighbors see each other, the one that has the highest router ID is going to become the active LDP router, and the one that has the lower router ID is going to be the passive LDP router from a negotiation perspective. So what this packet is showing us is that we have a TCP three-way handshake that's starting. Here's our SYN request. It's from the source transport address of R3, which is 3333, going to the transport address of R2, and that's the beginning of our three-way handshake. The next portion of our three-way handshake is from R2 to R3. Here's our SYNAC. And then we have our final acknowledgement right here in currently packet 19. So the three-way handshake has been established. From a TCP perspective, we now start the initialization of our LDP session. Again, it starts from R3 going to R2. We have a reply coming back from R2 to R3. That's here in packet 21. And then we have a keep alive message from R3 to R2 basically saying, you know what? We are good to go. LDP has been established. And then those two guys go crazy in exchanging their label mappings. So this is R3 saying, hey, here's all the labels I have and the associated networks I've mapped them to. And then R2 says to R3, hey, here's all the labels that I currently have and here's the prefixes that they're mapped to. And the cool thing is we're going to use a destination TCP port for this LDP session also of 646. So up here, if we look at the first SYN request going from R3 to R2, you'll notice it's from some random high-numbered port on R3 going to the well-known port of 646 for LDP. And that's where the session will be. So whoever starts the session, whoever initializes it, the device with the higher LDP router ID, is going to have a high-numbered selected port, and the router we're connecting to, the passive router, is going to have the connection at the well-known port of 646. So what we can do with that is, we can go ahead and say, you know what, I want to find any destination ports of TCP with port 646, right-click on that, and say I want to prepare a filter for that too, and we'll say or selected, and that adds it to our filter. Now for the replies back, which is packet 18, it's going to be a source port of 646. So I'm going to select that, right-click on it, and I'm also going to prepare that as a filter and say or to that as well. And what that'll effectively do, that'll capture just the LDP messages, hellos, and session messages that are currently present in this capture. And to apply that, we'll simply click on Apply. And that gives us a nice clear picture of just LDP. The other thing I'd like to do is I'm going to save this for us with just these packets. So to do that, with just this filter in place, I'm going to go to File in Wireshark. We'll say Export Specified Packets right here. And we'll call this Live LDP Capture from class. And it's showing us right here that although the capture has 37 packets in it, the displayed packets are just 22, and just those 22 packets are going to be in this new capture file. So I'll go ahead and save that. And just for a moment, I'm going to check my Nugget Lab folder just to make sure it really got there. So there it is right there, the live LDP capture from class. And the one above it, LDP negotiations, is one I did earlier today. If you want to refer to that as well, I'll put them both in the Nugget Lab files for you. So now that I know I have that file, let me go ahead and close this Wireshark output. I'm going to say quit without saving. Let's go back to that capture that you now have in the Nugget Lab files. We'll open that up. And that way, whatever we're looking at together right here, you will have an identical opportunity to look at from the Nugget Lab files. So packets 1 through 7 are all simply hello messages. Packet 8 is a TCP SYN request from R3 to R2. There's the SYN-ACK and the ACK. Here's our initialization message. Here's the reply back from that initialization request. There's the keep alive from the active LDP router. And then we have the exchange. So from R3's perspective, if we open up the details of this packet, what exactly are you sharing? I can go down here to the payload, and I'll scroll up just a little bit. And let's open up all of these. Let's expand. I'm going to right-click on LDP and say, please expand subtrees. It'll open up every single portion. And what I'd like to do is let's scroll down through all of this output, and let's look for a 5555. And here it is. So regarding prefix 5555, it's specifying in the label information that it has associated the local label of 309 in this advertisement that we're sending out to R2, that's our local label. Now if we go back to our router interface, we might say, wait Keith, wait, I thought the local label was 304, but remember we disabled MPLS IP, we brought it back up, and so it had the opportunity to choose whatever label it wanted to for that network. So if you and I hit the up arrow a few times and do a show MPLS LDP bindings for 5555, press enter, sure enough, it really does have MPLS label 309 as a local label. And that's the one that it's advertising for 5555 to R2 through the LDP session. And I would encourage you to do the same exact practice in your lab. Bring up Wireshark, disable and restart MPLS, capture that traffic, and then look at the details of it to determine what the labels are that are being advertised, and then use the CLI to confirm that information. And that, my friend, will greatly improve your skills, both at the command line with the commands to use to verify the labels, as well as the Wireshark tools to help verify what the actual packets are saying as they're going back and forth. And they should correlate between the two. So going back to our capture, we know a couple things. The hello messages happen on UDP using port 646 for source and destination. The actual sessions are TCP, however they do use the same destination port when initializing that connection, from the active LDP router to the passive LDP router. And then once they have a session established, they'll go ahead and exchange their label mappings with each other over that LDP session. We can also verify the neighborships right here on R3 just by doing a show MPLS LDP neighbor. It'll show us exactly who our neighbors are. So R3 has two neighbors, one who has an identity of 2222 using system-wide label space, and the other is 4444, also using system-wide label space. The ports in used for the session between R3 and R2 is port 646 on R2 and port 37442 for the session on R3. And that's because R3 was the active LDP router, has the higher LDP ID, so it initiated the session over to R2. For the session between R3 and R4, the ports in use are 16042. I just selected a high unused port, and on router 3 we're using the well-known port of 646. Why is that? And that's because R4 had the higher router ID from an LDP perspective. It initiated the connection to the well-known port of 646. This also shows us where we learned about that neighbor. For example, R3 is saying, hey, I learned about R2, my good buddy 2222. I learned about him because I saw his hello message coming from 10.23.0.2, and I learned it on my gig 2/0. He also says I learned about 4444, that good friend, because he sent hello messages that I saw coming from 10.34.0.4, and I saw those hellos on my gig 3/0. So the hello messages are from the actual interface itself IP address to 224.0.0.2, so interface to multicast address, and the actual session is from the transport address to transport address. And the hellos are UDP and the sessions are TCP. And for the hellos we use port 646 on both sides, and for the TCP session we're going to use the destination port of 646 for that connection to the passive LDP router between the two of them. While the source port for the TCP session is going to be whatever high numbered unused port that the active router chose to use for that session. And there's also going to be keep alives periodically to keep that TCP session open. Now, what could go wrong with an LDP neighborship, why it might not establish, is this. Let's say R2 is advertising little hello messages periodically. R3 sees that, and inside of these hello messages, it has the transport address of R2. And let's say, for example, that transport address is 2.2.2.2. So R3 would go ahead and say, wow, cool, I got somebody out here. I'm going to go ahead and do a three-way handshake and become LDP neighbors with this device. However, if R3 heard these hellos on interface gig 2.0, and for whatever reason, if R3 thought that this was the interface to use to get to 2.2.2.2, it's going to say, not going to do it. I'm seeing the hello messages on gig 2.0. They're sourced from 10.23.0.2, which is the interface of R2, but the transport address inside of that little hello message is showing a transport address of 2222, and this interface right here is not the right interface personally that I would use to get to 2.2.2.2. I will not form an adjacency. I will not become LDP neighbors with R2 because the interface I'm seeing the hello messages on is not the same interface I would use to reach the transport address that's being advertised in those hello messages. So let's demonstrate that. Let me bring up our routers again. And on R3, this is not a very nice trick to play, but I'm going to go ahead and tell R3 that to reach 2.2.2.2, it should go ahead and use R4 as its next hop. At the moment, it currently believes that to reach 2.2.2.2, it should go over to R2. And we can verify that with a quick look at the routing table. So we'll just say, please show me your routing table based on SPF routes you've learned. And right here we see that to get to 2222, the next hop would be 10.23.0.2, and the egress interface would be gig 2.0, which is perfectly how it should be. However, if we did something really mean, like created a static route that said, hey, to get to 2222, go ahead and send it over to R4, that would mess up the LDP. So let's do a couple things here. On R3, we'll go ahead and add that static route, saying to get to 2222, your next hop is going to be 10.34.0.4, which is R4. We'll disable MPLS, we'll re-enable MPLS, and we'll see which neighborship comes back up. So R4 came up, that's great news. So R4 is happy. But we are not going to get that neighborship with R2. It's simply because the transport address that R2 is sending in his hellos, R3 doesn't believe that's the right interface to go ahead and use to reach R2. And because R3 doesn't believe that that transport address is reachable or the best path on gig 2/0, it won't use it. Now we do have some commands that we can actually use to tell R2, hey, please advertise a different transport address. And by doing so, we could work around that. But the default behavior is really important to know, because if you have an asymmetrical routing environment, or for whatever reason, this interface on gig 2.0 isn't the best one to reach the transport address advertised in R2's hellos, your LDP is not going to work out of the box. So let's do a show MPLS LDP neighbor just to verify that we have one neighbor and R2 is no longer a neighbor with us. And just out of fairness, let's go ahead and take off that static route that's going the wrong direction. And once we remove that and the OSPF learned route is back in the routing table, we see the hello messages coming in from R2, we should immediately be able to go ahead and negotiate and establish that LDP neighborship. And there it is. So now if we use the up arrow key a few times and show our MPLS LDP neighbors, we've got router 4 and router 2 both back up and happy. Your action item, my friend, is to practice what you've seen. And I would do it all. I would actually do